When studying credibility estimators, it is insightful to have the following fundamental result from mathematical statistics in mind. When searching for the estimator of an unknown random variable y, using other random variables x1 until xn, the estimator for y that results in minimum mean squared error is the conditional expectation of y given these random variables x1 until xn. Let us work through the derivation of this result to refresh your understanding of this result from mathematical statistics. Assume y tilde is another estimator of this unknown random variable y, which is also built from the available random variables x1 until xn. Let us start from the mean squared error when using y tilde as an estimator for y. In the first equation, we manipulate this expression by bringing in y hat without changing the expression for the mean squared error. Recall that y hat is the conditional expectation of y given the random variables x1 until xn. Working out the square, the expression in the second equation results. And here we can show that the middle term in this expression, that is, the expected value of the product of y tilde minus y hat and y minus y hat, will be 0. And we will show this result on the next sheet. Putting things together, we conclude here that estimator y tilde must have a higher mean squared error than the estimator for y, than the estimator y hat for the random variable y. So the last step to focus on is the expression for the expected value of the following product of differences, namely the difference between y tilde and y hat on the one hand and y tilde on the other hand. Working out this expression brings us the second equation that you see appearing now on the screen. In this expression, we first focus on the expected value of y tilde multiplied with y. Applying the tau rule, it is straightforward to see that this reduces to the expected value of y hat squared. Hence, this term cancels out in the above expression. Next, we consider the expected value of y tilde times y. Again, applying the tau rule shows that this equals the expected value of y hat times y tilde, which again cancels out in the above expression. Putting things together, the expected value of the difference between y tilde and y hat on the one hand and y hat on the other hand is 0, which completes the proof. So what did you learn so far? Well, starting from the Poisson credibility model assumptions, you derived an expression for the conditional distribution of the risk random variable theta, conditional on the reported claims ni1 until niti reported by policyholder I. Next, you retrieved the predictive distribution of niti plus 1, that is the number of claims reported by policyholder I in a next time period. We are now ready to translate this knowledge into a so-called credibility premium, also referred to as the Bayesian credibility premium or the a posteriori premium. From the a priori pricing model, you already know what the expected number of claims in period ti plus 1 will be. That is, in our notation, lambda I ti plus 1. And the question that remains is, how should I estimate the unknown risk parameter theta I? Here too, you look at the following problem. You want to propose an estimator for theta I that is a function of the random variables ni1 until niti, the random variables expressing the claim history on policyholder I. More specifically, the estimator you propose for theta I should be as close as possible to theta I when using a quadratic loss function. Thus, you want the estimator to minimize the following mean squared error. Now we know from the property demonstrated on the previous two sheets that the estimator we are looking for is then the conditional expectation of theta given the random variables ni1 until niti. Thus, the estimator we are looking for is the mean of the posterior distribution of theta given the reported claim history. And we use this posterior mean because it minimizes the quadratic loss function that expresses the mean squared error. Since we want to use the posterior mean of theta in our experience rating setup or credibility setup, we need to find a workable expression for this posterior mean. The extra notes in the lecture material show you how to derive the expression printed on this sheet, and you should study this derivation at this point in the course. Important to notice here is the fact that the posterior mean only depends on the total number of claims reported by policyholder I, denoted here with KI bullet. This is the total number of claims reported by policyholder I over the past TI years of insurance. The fact that the age or timing of past claims is not taken into account, but only the total number of claims matters, is a typical feature of so-called static credibility models, of which our Poisson credibility model is an example. The random effect or random risk variable theta does not change over time, hence the static feature of this particular credibility model. So combining the estimator for the random risk parameter theta I with the a priori mean for niti plus 1, we find the Bayesian credibility premium for niti plus 1. And we find this credibility premium as the expected value of ni in the next time period, conditional on the claims reported in the past. Rewriting this expression by either applying the Tower rule or by working with the predictive distribution of niti plus 1, we find the so-called Bayesian credibility premium. And this is the posterior expected claim number. Linking this with our earlier comments on financial equilibrium, it is insightful to notice that, on average, the posterior corrections are equal to 1. As such, the posterior corrections are balanced. Some policyholders will get a discount and some will be penalized based on past claiming behavior. But overall, the a priori premium volume will not be changed. You can see this by calculating the average of the posterior corrections. Policyholder I's posterior correction is the expected value of the risk random variable given the reported claim history. Using the Tower rule and the assumption of unit mean of the random variable theta, we see that on average the a posteriori corrections have mean 1.